Hi there and welcome to another video from me, Mr. Arnold. We're going to look at the Poisson distribution in this video, which is on the Edexcel S2 A-level module. This is our second tutorial on a crash course towards the exam. And as always, if you're looking for further help with your studies, do check out youtube.com/Mr. Arnold's Maths, and please do follow me on Twitter at Mr. Arnold's Maths. Okay, so the Poisson distribution. Really quickly, we're just going to start off with the conditions of a Poisson distribution. And again, you must learn these a little bit like the binomial. So the first thing that we've got to know is that events must occur one at a time, or singly in space or time. So they must occur one at a time. All events must be independent of each other. Events must occur at a constant rate, and rate is going to be hugely important in identifying Poisson distributions. And then finally, events must occur randomly. So just really quickly, this is an exam question from June 2010, and it says here: a company has a large number of regular users logging onto its website, on average 4 users every hour, so there's your rate, failed to connect to the company's website at their first attempt. Part A, explain why the Poisson distribution may be suitable in this case. So, I mean, any of the 4 conditions we spoke about, I would say here that events occur at a constant rate, but you can use any of the 4 conditions we spoke about. Okay, so here is the formula for a Poisson distribution. So we say X is distributed such that it has a Poisson distribution with parameter lambda. Now, lambda is like the rate. Okay, and the formula, which is given in the formula book, says that the probability that X equals E to the power of minus lambda times lambda to the power of x over x factorial, and that is given in your formula book as well, exactly as I have it written here. So suppose I want to I'm told that a random variable x is distributed with a Poisson distribution with parameter 3.6. Find the probability that x equals 5. Well, what we're going to do is just plug it into the formula. So that's going to be equal to e to the power of minus 3.6, because lambda is 3.6, times by 3.6 to the power of 5 over 5 factorial, close off our brackets, plug that into your calculator, and when you do that, you should get to 3 significant figures: 0.138. Next part, the probability that x is greater than 3 but less than or equal to 6. So if we think about this quite carefully, that is going to be the same as the probability that x is equal to 4 plus the probability that x is equal to 5 plus the probability that x is equal to 6. So again, what we're going to do is plug each of these into our formula. This is going to be a wee bit longer. So here we go. We've got e to the power of minus 3.6 times 3.6 to the power of 4 over 4 factorial, plus e to the minus 3.6 times 3.6 to the power of 5 over 5 factorial, plus e to the minus 3.6 to the times 3.6 to the power of 6 over 6 factorial. And what I'm going to do here, I'll just scroll down the page a little bit. I'm going to factor out e to the power of minus 3.6 just to enable me to input it into the calculator a little bit easier. E to the minus 3.6 times by 3.6 to the power of 4 over 4 factorial, plus 3.6 to the power of 5 over 5 factorial, plus 3.6 to the power of 6 over 6 factorial, close off the brackets, enter that into your calculator just as we see it there, and when you do that to 3 significant figures we get an answer of 0.412. Okay, and maybe you might want to pause the video and try this one here. So see if you can work out the probability that x is less than 2. Alright, hopefully you've had a go at that. What you should have done is worked out the probability that x is equal to 1 and added the probability that x is equal to 0. I really should have put those in the other, in a different order, but hey, it's not that important. So the probability that x equals 0 plus the probability that x equals 1, again inputting them into your formula, and you should get an answer of 0.126 to 3 significant figures. Okay, let's crack on now and have a look at an exam question. So this is from January 2010 and it's question 3. So a robot is programmed to build cars on a production line. It says the robot breaks down at a random rate of once every 20 hours. So it's once every 20 hours. Find the probability that it will work continuously for 5 hours without a breakdown. Now the important thing to consider here is lambda. Remember, lambda is constant for Poisson distributions. So if it breaks down once in 20 hours, well then in 5 hours, lambda should be 0.25. So it breaks down once in 20 hours. In a quarter of the time, the rate should be a quarter, so it will break down 0.25 times. So lambda is 0.25 here. So I want the probability that it will work continuously for 5 hours without a breakdown. So what I'm saying here now is that I want the probability that x is equal to 0. X is the random variable that the robot breaks down. So if it doesn't break down, that means the probability of x equal to 0. So we're going to put this into our formula now. So we get e to the minus 0.25 times 0.25 to the power 0 over 0 factorial, which in fact, well, that's just 1 divided by 1, which is 1. So it's e to the minus 0.25. And when you plug that into your calculator, you should get an answer of 0.7785. 0.7785. Okay, second part, it says find the probability that in an 8-hour period, the robot will break down at least once. Again, we've got to think of this in terms of rates. So if it breaks down once in every 20 hours, in 8 hours, the rate will be 0.4. 0.4. So I want the probability that the robot will break down at least once. So the probability that it breaks down at least once means it's greater than or equal to 1. And that must be the same as 1 minus the probability that it doesn't break down, that x is equal to 0. Okay, very important here. Remember, lambda has changed. So when we plug that into our formula, we should be doing 1 minus e to the minus 0.4 times by 0.4 to the power of 0 over 0 factorial. Plugging that into your calculator, you get an answer of 0.3297. 0.3297. So just once again, the important part here is that lambda has changed, okay? If it breaks down once in 20 hours, well then in 4 hours, it would break down 0.2 times. So in 8 hours, it would be 0.4 times. Okay, next part. There are exactly 2 breakdowns. So I want the probability that the number of breakdowns is exactly 2. Remember, x is the random variable that the robot breaks down. So we're going to do e to the power of minus 0.4, again utilising the formula, which is in the formula book, to the power of times 0.4 squared over 2 factorial. Again, plugging that into your calculator, you should get an answer of 0.0536. 0.0536. Okay, and the final part of this question says, in a particular 8-hour period, the robot broke down twice. So we know what that probability is, 0.0536. It says now, write down the probability that the robot will break down in the following 8-hour period and give a reason for your answer. Well, this is where we've got to remember what our conditions are. And one of the conditions was that the events are independent. So it doesn't matter that it broke down previously. The probability that it will break down in the next 8-hour period is exactly the same. So the probability must still be 0.0536. And the reason are that they're independent. Independent. Okay. Poisson distribution, all events are independent. Okay, let's move on now to the next part of this video, which is going to be all about using the tables. So this is what your tables look like. Quite similar to what before. Remember, they're cumulative tables, so they tell me the probability that x is less than or equal to a particular value of x. So let's just have a look at the example and we get an idea of how to utilize these tables. Okay, so I've got a random variable x that has a Poisson distribution with parameter 2. And what I want to do is I want to work out the probability that x is less than or equal to 4. So, first thing we're going to do is we're going to find where lambda is 2. So I look along my table, I see that lambda is 2 here, and I want the probability that x is less than or equal to 4, which is here. So we've got lambda 2, and the particular value of x is 4, so we're looking at 0.9473. So it's 0.9473. The next part, which asks me the probability that x is equal to 3. Now suppose I didn't want to use the formula, which would actually be a little bit easier in this case. I could do it using the tables, but I must remember that that's cumulative, so that's going to be the same as the probability that x is less than or equal to 3 minus the probability that x is less than or equal to 2. And that will tell me the probability that x equals 3. Well, reading off from my table, less than or equal to 3 is 0.8571. 0.8571. Take away the probability that x is less than or equal to 2, which is 0.6767. 0.6767. And again, when we work that out on our calculator, we get a value of 0.1804. 1804. Okay, maybe you want to pause the video and try these two. I'm going to crack on ahead with it now. The probability that x is greater than 2, remember these are for less than or equal to values of x. Well, that is going to be the same as 1 minus the probability that x is less than or equal to 2, which is 1 minus 0.6767, and again, bashing that into the calculator, we get 0.3233, 0.3233. And then the final part, the probability that x is bigger than or equal to 3 but less than 7, which means it's going to be the probability that x is less than or equal to 6, take away the probability that x is less than or equal to 2. And when we work that out on our calculator, we get a value of 0.3188. 0.3188. Okay, so let's just move on now. So we've got an idea of how to read the tables. I've got an important piece of information next, which is all about the mean and the variance. And this is an assumption of, well, we can think of it as an assumption of the Poisson distribution. So the mean of x, if it has a Poisson distribution, is equal to lambda. And the variance is also equal to lambda. So if the mean and the variance of a random variable are very, very close to each other, then we can assume that it has a Poisson distribution. And that's going to come in useful a little bit later on. Let's have a look at an example here. So this is going to utilize what we've been doing with the tables. So breakdowns on a particular machine occur at a random rate of 1.5 per week. It says find the probability that no more than 2 breakdowns occur in a randomly chosen week. So no more than 2. And remember, in this case, in part A, lambda is going to equal 1.5 because we're talking about per week here. So a chosen week, 1.5 for lambda. Find the probability that no more than 2 breakdowns occur. So what we're looking for is the probability that x, if x is a breakdown, is less than or equal to 2. So the probability that x is less than or equal to 2 when lambda is 1.5. So no more than 2, which means it's either 2, 1 or 0. Here's where our tables come in useful. So lambda 1.5 and less than or equal to 2. We don't want to do that. So lambda equal to 1.5 less than or equal to 2, 0.8088. 0.8088. Part B. Find the probability of at least 5 breakdowns in a randomly chosen 2-week period. Now this bit is really, really important. In a 2-week period, remember, they occur at a constant rate. So if lambda was 1.5 for 1 week, for 2 weeks, lambda is going to equal 3. So we can write it like this. Let's be fancy and write it this way. My random variable has a Poisson distribution with parameter now of 3. Okay, if it's 1.5 in 1 week, in 2 weeks it's going to be 3. Now we want at least 5, so I want the probability that our random variable has at least 5. That means it's got to be greater than or equal to 5. Now that must be the same as 1 minus the probability that it's less than or equal to 4. Less than or equal to 4. So again, we go to our tables. So opening up our tables, lambda now is 3. Lambda is 3, and we want less than or equal to 4, 0.8153. 0.8153. 0.8153. Bash that into your calculator and then you get an answer of 0.1847. Okay, the final part of the question. A maintenance firm offers a contract for repairing breakdowns over a 6-week period. The firm will give a full refund if there are no more than n breakdowns in a 6-week period. The firm wants the probability of having to pay a refund to be 5% or less. So if there is more than n, we get a refund. And I want that probability to be less than or equal to 5. So essentially what we're saying here is, I want the probability that the number of breakdowns is going to be, if there's more than, so greater than or equal to n, that's got to be less than or equal to 0.05 because it's 5% or less. Now, remember our tables do less than or equal to, so if more than n is got to be less than or equal to 0.05, that means the probability that x is less than or equal to n, so the minimum number, must be less than or equal to 0.95. It's got to be 95%. So what we do is we go to our tables again. And remember, it's a 6-week period. Now, if it's a 6-week period, 1.5 per week, that means 3 for every 2 weeks, which means lambda is got to be equal to 9. I should have cleared that up first time round. So lambda's got to be 9 here. And let's just scroll down. Lambda's got to be 9. And I've got to see what value of n do we cross into that 95% range. And here we are here. We see here at 13, it's below 95%. And then once we get into 14, we're over the 95% threshold, which means n must be 14. So n is equal to 14. Okay, tricky example that. Let's have a look at another one. So, on a typical summer's day, a boat company hires rowing boats at a rate of 9 per hour. So, currently, we have a Poisson distribution. Yeah, remember, per hour, it's a rate. And it's 9 per hour. Find the probability of hiring at least 6 boats in a randomly selected 30-minute period. So if it's 9 per hour in 30 minutes, that means my lambda is going to be 4.5. So x has a Poisson distribution with parameter 4.5. And what we want here is, I want the probability of at least 6 boats, which means it's got to be greater than or equal to 6. So part A, I want the probability that x is greater than or equal to 6. So what we do is, our tables don't tell us greater than or equal to 6. That's going to be the same as 1 minus the probability that x is less than or equal to 5. So that's 1 minus, and let's go to our tables. So remembering lambda here is 4.5. Lambda is 4.5, and we want less than or equal to 5, which is here, which is 0.7029. So 0.7029. And when we put that into our calculator, we get 0.2971. Now, maybe at this point you want to have a go at part B. Feel free to have a go, pause the video and see if you can get the answer. The company has 8 boats to hire and decides to hire them out for 20-minute periods. So if it was an hour, 20 minutes is 1/3 of an hour, which means the rate must be 1/3, which means lambda is now going to be 3. So lambda is going to be equal to 3 here. Show that the probability of running out of boats is less than 1%. So I need to show that the probability that x is bigger than 8, because they've only got 8 boats, must be less than 1%, 0.01. So I need to show that. So, well, the probability that x is bigger than 8 is going to be the same as 1 minus the probability that x is less than or equal to 8. So let's go to our tables. Remember, lambda is 3. So lambda is 3. Less than or equal to 8 is here, 0.9962. 0.9962. 9962, which equals 0.0038, and you can clearly see 0.0038 is less than 0.01, so we've shown that. And then the final part says, find how many boats the company should have to be 99% sure of meeting all demands if the hire period is extended to 30 minutes. Well, if the hire period is extended to 30 minutes, that means x is going to have a Poisson distribution with parameter of 4.5 now. 4.5. If the rate is 9 per hour, well, in every half hour it must be half the time, half the number of boats, so it will be 4.5 boats per hour. So, if the probability that x is greater than n, which is the number of boats, is equal to 0.01, well that implies that the probability that x is less than n must be greater than 0.99. So what we're going to do is we're going to go to our tables and look for lambda equal to 4.5. Lambda 4.5. Now where does it go over 0.99 in this region here? So when we get to 10 boats, we're good. So n must be equal to 10. Alright, let's move on. An exam question here. So this is from June 2010. It's question 5 part B. A company has a large number of regular users logging onto its website. On average, 4 users every hour fail to connect to the company's website at their first attempt. So what it's telling us is that we have a random variable. Remember, every hour implies a rate, and a rate implies Poisson distribution. So currently, lambda is 4. It says find the probability that in a randomly chosen 2-hour period, so if it's 4 users every hour, well that means every 2 hours, lambda must be 8. So what we'll say now is that x has a Poisson distribution with parameter 8. And what we need to do is find the probability that all users connect at their first attempt. What we have to remember is that x is the random variable that they fail to connect. So if x is the random variable that they fail to connect, I want the probability that they fail to connect, or that no one fails to connect, should I say. So what we're going to do here is go straight to our tables. Lambda is 8. So let's just scroll down here. Lambda is 8, and I want the probability that x is equal to 0 here, which is 0.0003. 0.0003. And then the second part, at least 4 users fail to connect. At least 4. So I'm looking for the probability that x is at least 4 means greater than or equal to 4, which is going to be the same as 1 minus the probability that x is less than or equal to 3, which is going to be 1 minus, and let's go to our tables again, so less than or equal to 3.0424, 0.424, and when we work that out in our calculator we get 0.9576. Okay, another exam question. A cafe serves breakfast every morning. Customers arrive for breakfast at random at a rate of 1 every 6 minutes. Now that's our current rate. Find the probability that fewer than 9 customers arrive for breakfast on a Monday morning between 10 and 11 a.m. So if it's 1 every 6 minutes, in an hour we should have 10 people. So what we could say here is that x has a Poisson distribution with parameter 10. So x has a Poisson distribution with parameter 10. Fewer than 9. Well, that's going to be less than or equal to 8. So I want the probability that x is less than or equal to 8 when my parameter is 10. Let's go to our table. When lambda is 10, less than or equal to 8 is 0.3328. Not 0.3328. So fewer than 9 is got to be 8 or less, which is 0.3328, and we're done. Okay, important thing here. Sometimes what we can do is we can approximate a binomial distribution by using the Poisson distribution. So just a reminder, if x has a binomial distribution with n trials and the probability of success being p, well, If n is large and p is small, then what we can do is we can approximate it. And what we say is we'll approximate it using a Poisson distribution such that the parameter is n p. Where that comes from is the fact that in a Poisson distribution, lambda equals the mean mu, and in a binomial distribution, the mean mu comes from the fact that that's the same as doing n times p. So let's have a look at this in action now. June 2008, question 4, part C. So each cell of a certain animal contains 11,000 genes. It is known that each gene has a probability of 0.0005 of being damaged. Using a suitable approximation, find the probability that there are at most 2 damaged genes in a cell. Well, n is very, very large here, and p is very, very small. So what we can do is we can approximate it by using the binomial distribution. So we're saying x is going to have a Poisson distribution with parameter np. So np was actually calculated in a previous example. It was actually done in the first video. Gives us 5.5. So x has a Poisson distribution parameter 5.5. So I want the probability that there are at most 2 damaged cells. So at most. So I want the probability that x must be less than or equal to 2. So that's at most. And let's go to our tables here. So parameter 5.5 less than or equal to 2, which is 0.0884. Not 0.0884. Okay, and that's it for this video. Quite a quick one there, but hopefully you found it useful. I'll be back again soon with another video. I'll talk to you again sometime.